Okay, hello. This is the theory for chapter 7, which is work and energy. Also, there's a question about conservation energy, which is, whatchamacallit, chapter 8. So that's mixed in here as well. Actually, I'm going to put that in the other video. So forget that question existed. I'll put that in the chapter 8 video. Anyways, so this can go away as well. Let us begin this with this question here, question 1. So an elastic bungee cord does not obey Hooke's law. When stretched a distance s beyond its relaxed length, the cord exerts a conservative force F equals negative ks minus alpha s cubed. K and alpha are constants. What is the equation for the elastic potential energy of the cord as a function of s, given algebraic expression in terms of k, alpha, and s? Okay, so A. Also, this can go away. Anyways, A. So we need to understand that when a spring is stretched from its resting length, right, we're going to get negative delta V. That's what happens, right? And using the fact that, so we're going to use this fact that U is equal to negative delta V, right? And, well, it starts at its relaxed length. And from the theory video, we know that relaxed length is just, relaxed length is just zero potential energy. So we're going to have that the work is negative VF. Or in this case, we can call VF VC, which is what it is in the problem statement. So we know that U is equal to the integral of F ds. So we have that U is equal to the integral of F, which is this, ds. And if we integrate this, we're going to get negative ks squared over 2 minus alpha s to the 4 over 4. Or not minus, sorry. This is plus alpha s to the 4 over 4. And then, well, we know that negative v is equal to u. So that means v is equal to negative u. So to get our final VC, or v is a function of s, we're going to have ks squared over 2 minus alpha, okay, I love making typos, minus alpha s to the 4 over 4. And that is our Vs, which we have gotten just from understanding that work is negative delta V in this situation because it is being stretched. And then, yeah, when stretched, it says here it's stretched. So using that and the fact that U is equal to the integral of force ds, which we then integrate, and then plugging it into this relationship here. And for B, we need to, the cord has a relaxed length L sharp equals 30 meters, let K equals 35 newtons per meter, and alpha equal 0.002 newton meter to the negative 3. A 65 kilogram bungee jumper is attached to the cord and then jumps off a bridge. Determine her speed when she has fallen a total distance of L equals 80 meters, where L is equal to L sharp plus S. Okay, so to do this, well, okay, this is also, this part of the question uses conservation of energy, which is supposed to be chapter 8, but that's okay. I'll leave this part in anyways. So it's T1 V1 plus V1 equals T2 plus V2, like this. We know that V1 is going to be a height of a height of 80. We know that there's no kinetic energy at first because before she jumps, right, she's just standing there, right? So you have 0 plus mgl is equal to, now T2 is half mv squared, right? Because he has a velocity at this point, which we're trying to actually solve for, plus this potential energy from the cord. Now, there's also going to be a gravitational potential energy that we ignore because we're going to say that she's fallen from 80 up down to 0 up, right? So we can write it as plus mg0 where the height is 0, so we can just ignore that term. Now, and also ignore this 0 here. We get this, we want v. So we do the rearrangement to get the v is equal to the square root of, let me see, minus k thing plus alpha thing divide by half m. Okay, so it's equal to 2gl minus ks squared over m. And when you divide by a half here, the half for that cancels, plus alpha s to the 4 over 2 m is equal to v, right? And so now we need to plug in our numbers. Square root of 2 times g 9.81 times l 80 minus k 35 times s squared. S is 50. 50 squared over m of, what is m? 65 kilograms. Over 65 plus alpha is 0.02 times s squared, so 50 to the power of 4, not squared, over 2 times 65, which gives us a answer of 17.9 meters per second. So v is equal to 17.9 meters per second. And that is the question. Now, there was that other question, but I'm going to save that for the Chapter 8 problems video. So now we can move on to these questions here, the ones that are on this page. These are some good questions as well. So, okay. Bring to front. Bring to front. Okay, there. So, calculate the velocity of the 50 kilogram crate when it reaches the bottom of the chute at B, if it is given an initial velocity of 4 meters per second at A. Coefficient of kinetic friction is 30.3 and 15 degrees is the inclined slope. Sorry, is the incline angle. So we need to get some free body diagrams going, right? Well, we don't need to because this is energy. We don't really care about stuff like the forces and whatever, but we do for work if there is work to look at. So we know there's friction, so we'll have a opposing friction like so. Friction like this. We know there's going to be gravity like this, mg, which when we split into components, we're going to have down this way and down this way, which balances out the normal force. So the normal is equal to angle of 15 is here. Angle of 15 is here. So, yeah, okay. We know the velocity. We know there's friction. Okay, so we're going to be using for this the principles of work and energy, right? So I'm going to call that PWE, principles of work and energy, right? So we have T at A plus the non-conservative work is equal to t at b. And this is how we get speed, by the way, because this is half mv squared and this is half mv squared. So let's look for what u is. We have two things that will be part of u. We have friction plus weight. Okay, so for friction, we'll call it UF. That is going to be equal to the integral, of course, of f cosine theta ds, where our angle theta is 180. If you look at it this way, the path is this way, so there's a full angle like this of 180. So, and then the force of friction is mu n, which we know. We need to also solve for n, but we'll do that after. So this is equal to the integral of negative mu n ds. Like so, mu and n are constants. So now we know that delta s is 10. So yeah, we can just call this negative 10. Mu is 0.3, so we can call it 3. Negative 3n. That is what we need here. Unless I did my integration wrong. I don't think I did, though. No, I didn't. It's fine. Okay, so now we need to get n. So to get n, we, like I said earlier, we used this, like so, to get n off the diagram. Now, when you're solving these questions, do make free body diagrams. I know I said we don't need to, but that was a mistake of my mind speaking before I actually thought about what I was going to say. Make a free body diagram. I kind of skipped through that and made it here. So I don't know why there's two n's. This is, well, I mean, yeah, this is also n because they're equal. This is not supposed to say n though. Can I erase just that? Just that. There we go. Yeah, so there's n is equal to mg cosine 15. There's theta cosine 15. So n is equal to mg cosine 15. So we can take this and plug it into our equation like so, which gives us a value of, let me see, negative 3 times 9.81 times mass 50 cosine 15, negative 1421. Negative 1421. Yeah. Okay, so now we need the work due to gravity, so UW, which is just equal to, again, you would do the integral, but we can skip that because we know what this is, which is mg delta y. And so we know it's negative 50 times 9.81 times, oh, why did it do that? Times 9.81 times, what? How do I stop that? Okay, I guess that's just italicized now. Times 9.81 times delta y is, we our change in y from here to here is just 10 meters as a hypotenuse times this here, which is opposite, so 10 sine 15. Is this still italicized? Okay, no, good. So UW is equal to, let's see, negative 50 times 9.81 times 10 sine 15 is negative 1270. 1270. And these are in joules, by the way. Both of these are in joules. Right? So now we can go to our this equation here and solve. So TA is half mv squared, so a half times 50 times v squared, so 16. So we can just simplify this to 8 times 50. which we can then simplify to 400. So that's 400 plus negative 1421 minus 1270, which is equal to, so we have TB, which is a half, M is 50, so 25 V squared. So we're going to go 400 minus 1269 minus 1421, divide by 25. And the negatives would have canceled out, of course. Because, yeah. I think I made a mistake here. Because, yeah. There was a mistake made. Okay, so what did I screw up here? Negative mg. Oh yeah, this is supposed to be plus. The direction of this is negative, so it's plus 1270. Okay, I figured out what the error was here. So we got 400 plus 1270 minus 1420, and then divide this by 25, and then take the square root, gives us a velocity of 3.15 meters per second. All right, originally I got a velocity of like, it was like 99, so square root of 99 is approximately 10, and that was a little too high because, yeah. So as you can see, keep track of your signs, and let me like space these out so that it's like sensical. But it's negative here, but the difference in y, we're going downwards, so the difference in y is also negative. So make sure you keep that in mind when doing these questions. Always check your signs before moving on to something else. Okay, so next question is, and this gone too, is this. So the crawler, whatever, constant speed of 2 miles an hour, brought to a stop suddenly. Compute the maximum angle through which the cable of the wrecking ball swings, and this is 20, that is inches, 20 inches. So it's constant energy, and then it becomes 0 sudden stop. So T1 is equal to half mv squared, and m is something. So we don't know m over 2. V squared is 4, but we should probably convert that. So 2 miles per hour, when you convert it to feet per second, is, I don't actually know. Let's see. 2 miles per hour to feet per second. 2.93. Okay. So times 2.93 squared. Just like that. Very nice. So we know that T2 is 0. Oh, we need to find U to do this. So we have work done by gravity for U, which is equal to, again, negative mg delta y, and then delta y we can just call y. If you look at theta here, it moves like this, right? So it is originally 20 inches, and then it becomes 20 inches cosine theta, right? If we imagine like this. So our delta y is 20 minus 20 cosine theta, like that. And we're solving for theta, right? So we know from our principle of work and energy, we know that we're going to have m over 2, and this is minus mg is equal to 0. So as you can see, the masses cancel out. So this becomes a half. Masses cancel out like that, right? And rearranging for cosine theta, we would get, so add this and then divide this by gravity, and then add 20 and divide by negative 20. Okay, So we would get a theta. So we get a cosine theta is equal to the stuff I just said. And these are all constants. So then we would get cosine theta is equal to, so we'd have a half 2.93 squared. And then we brought g, so over g. So I'm just going to call this 0.5 over g plus 20, or minus 20, divided by negative 20. So plus 1. And then this would be 0.5 or a half over, and so 1 over 40, which is 2 over 40 is 1 over 20, which is it's something, whatever. I don't want to do that in my head. 1 over 40, like that. And then so we just take theta is equal to the inverse of this, so inverse cosine of this. So we get 6.64 degrees. And so what is 1 over 40? Kind of, 0.025. I should have thought of that. I don't know why. 0.025, 2.93 squared, divide by 9.81, plus 1, and then we take the insert. Yeah, okay. I think I did the rearrangement wrong, maybe. Plus this, half 2.93 squared, divide by g, and then it's minus 20, and then divide by negative 20. Yeah, whatever. It's fine. This is what you're going to get for your final theta. I think I made an error in the rearrangement. But... oh yeah, I did. Wait, no, did I? I don't know. Whatever. That's your final answer for the question. I put it into my calculator, right? So that's what matters. I think I just did the rearrangement wrong. And I'm not seeing what is wrong. Probably this. Okay, I need to probably explain this. So you bring g cosine theta over to this side. So plus on this side. And then you divide by g. So this is half of 2g. And then you take away 20. And then you divide by negative 20, making this plus 1. Oh, I forgot to make this negative. That's what I forgot to write down. Okay, problem solved. So just bring back the original statement. This is supposed to be negative now. That's what I wrote wrong. Yeah, I don't know why I didn't notice that instantly. This becomes negative 1 over 40, which will then give you the right angle. Okay, last question is hidden over here. I need to like move the, here it is. Okay, so the 2 kilogram collar is released from rest at A and slides down the inclined fixed rod in the vertical plane. So this is our vertical plane. Coefficient of kinetic friction 0.4. Calculate velocity of the collar as it strikes the spring, so at this point, and the maximum deflection x of the spring. So that's from like kx squared, right? Half kx squared. So, or it's the work due to the spring, so whatever. So firstly, we will be looking at our, we can make a free body diagram, but like a pseudo free body. So we're going to have gravity, of course, straight down, which means, I'm just going to call it W for now. So, which means it's going to break into its components alongside these axes like this. So one component here, one component here. We're going to have the normal force that comes from the rod onto it, and like this. And we have friction pushing back like this, little f for friction, right? This is W. This is 30 degrees here. Yeah, so this is W cosine 30. Like that. Okay, there's our free body diagram. So, and then we can visualize when we hit the spring, it's going to compress down, right? So we're going to get an x that goes like this. And yeah, we need to get the velocity at this point. Anyways, that is that. So looking at our principle of work and energy, we have that T at A, well, T at A is not moving, right? Rest. So T at A is equal to 0. What is U from A to B? We need to calculate that. Is the work of gravity and the work of friction, right? So we'll start with the work of gravity, because this one's really easy. Is it's just mg and our distance. So I don't know why I'm blanking right now. Also, we'll need our normal force later, so we can get that now. As you can see, it's just equal to mg sine 30, which is a half. Very nice. Anyways, our distance here that we travel is 0.5. So that will be what we use for the work done by gravity for our distance. So it is mg, and this is specifically mg cosine 30, and then times 0.5 for the distance, right? That is what that is. And then this is just 0.5 times 0.5, so 0.5 squared. And then g is 9.81, m is 2. And 0.5 times 2, 1. So, okay, one of the 0.5s cancels with the mass. Like that. So this is g cosine 30. Makes putting it into the calculator easier. You can, yeah. And then we have, for the work done by friction, this is equal to, so we would do the integral thing and the distance, right? Friction goes this way, normal force, and yeah. So we would have negative mu, which is 0.4. We get n and 0.5. And then we replace n with mg sine of 30. And then we know that m is 2, so we can just get rid of the 2 and the 0.5 because of that. So there you go. And then now we need t at b, which is just half mv squared, and then we can get rid of the half m because m is 2, so it's just v squared. So putting this all together, we get g cosine 30 minus mu sine 30 equals v squared. So we're just taking the square root of this term. So the square root of 9.81 cosine 30 is a half minus 0.4 sine 30, which gives us a velocity of 1 I don't know where I got that from. 2 okay, I can't read. 2.56 v is equal to 2.56 meters per second, right? Because yeah, g cosine 30 minus mu g sine 30 is, and then we square root it. Yeah. Very nice. So that is from A to B. We got our velocity at B. Now we need to get our deflection of the spring, right? So if you consider this is our like area B, right? The second we hit it, like this is the velocity as it strikes the spring, and then now we need to get from B to C, where we have a spring work. So this was from A to B, and this is from B to C. So here we have a TB, which we already got as TB is just V squared. Nice and easy. And then, so yeah, 2.56 squared. So it's just 2.56 squared. And then we need to get a, we know that TC will be 0 because when the spring is maximum deflection of the spring, right, it's purely going to be spring energy, elastic potential energy, due to the fact that there will be no movement. So it'll just be work. So TC is equal to 0. And now we need to get work, which is due to weight. So UW plus U friction, because there's still friction on the rod, plus US for the spring. So we can get all of these. So UW is equal to mg cosine 30, and our displacement is going to be x. We don't know how far down we've gone, right? So the also keep in mind n from earlier. This one still applies. This normal force from here. So U of F is equal to mg sine 30 x, because we don't know the distance here either, right? And then US is equal to, so negative k over 2, and then we have an s squared, right? But the correct thing is delta s squared. But we know that since we're calculating s from C, I mean not from C, from B, right? This is 0, and then our maximum is x. So we can just replace this with x squared because the initial is just 0. So negative kx squared over 2, like so. Now we just need to use, again, our principle of work and energy, putting that together. So we'll have 2.56 squared. I forgot about this thing. Oops. 2.56 squared plus mg cosine 30x minus this term, because the friction is negative, minus this term, and then minus kx squared over 2. So this is yeah, half m cancels because half 2. And this is all equal to 0, right? So as you can see, mg cosine 30, mg sine 30, these are constants. So we'll have these two x terms that cancel out. K is 1.6, also constant, over 2 is 1.6 over 2.8. And then 2.56 squared also is a constant. So this is a quadratic. So I'm just going to quickly go 2 times 9.81 cos 30 minus sine 30. Oh, there's also where did I forget mu? I don't know where that went for the friction. Mu cosine 30 minus 0.4 sine 30, right? So 13x, and then we're just going to this is a quadratic, so use a quadratic solver or whatever on your calculator. So a is negative 0.8, b is the thing I just calculated, and then c is 2.56 squared, and that gives us an x of 99 0. Or what are we, 90? Okay, this is a really small number. When you convert it, we get an x is equal to 99 millimeters. So you get a very small x without. Another way you could have solved, I would just use the quadratic solver, because you get these two terms, mg cosine 30 and mg mu mg sine 30 attached to an x. And then you have your kx squared over 2, and a constant. So yeah, this is a nice quadratic that you can put into your calculator and get an x that gives you 99 millimeters. Anyways, is that the last question? Yeah, it is. So those are all the questions for chapter 7. Chapter 8 will have the conservation of energy. This one was just the principles of work and energy, right? So thank you for watching. Hope you learned something, and bye.